All right, welcome back. So this video and this section marks a pretty radical shift in the content of this course because we started out, and I guess that sounds scarier than it should be, but we started out talking about the general terms, money, the history of money, types of currencies, setting the stage for Bitcoin. Then we just wrapped up a quick intro to Bitcoin section where we basically talked about it at a high level. We showed an actual real world transaction. Now we're moving into the nitty gritty. We're going to talk about the underpinnings of Bitcoin, what actually makes it work.
And why we trust it.
Yes. And so this section is all focused on cryptography, the crypto part of cryptocurrency. So why do we care? Well, let's imagine we have 5 miners. We have a very small Bitcoin network here, and these miners are all in charge of maintaining the ledger. Now, if the ledger was just a text file or an Excel spreadsheet that anyone could go and just update at will, you could go back and edit something in the past. For example, let's say 3 of them decide we're going to get rid of that pink transaction. Whoever that was, we're erasing
That's
it.
Montana's.
Okay, sure, it's Montana.
We're deleting Montana's transaction.
So these 3 miners could get together and do that. And this is in the past, right? This has happened long ago. On our diagram, it doesn't look that long ago, but imagine this was 6 months ago. There's nothing stopping them unless there's some sort of cryptography involved. So how does cryptography relate to Bitcoin? How does it help us secure the ledger? How does it help us ensure integrity of our transactions? That's what we're talking about in this section. It's quite complicated, but pretty fascinating stuff. But let's start with a simple definition. What is cryptography, Kevin?
I don't know if this is a definition, but this is the etymological root of cryptography. It's Greek for secret writing.
Okay. Well, my dumb definition that I like is that it is the art and science of secure communication in the presence of an adversary.
It's a good one.
So basically it means, I like to think of it as just really fascinating and challenging word puzzles and games because a lot of the cryptography stuff that we'll talk about is pretty interesting. It's cool stuff, but it's developed and its roots are in war most of the time, in wartime.
War or politics.
Or politics, being able to write a message in the presence of an adversary and get it to some ally somewhere and have them be able to understand it without, somebody intercepting it shouldn't be able to understand it or read it right away or make sense of it.
So let's get into a simple example. So the one that you might intuitively know if you were to come up with cryptography on your own is called a Caesar cipher. And this is the one, Julius Caesar was credited with inventing this. I'm not sure if he did, but it's been around for a long time. And it's basically, you have this thing called a cipher. And this is a code right here. So we can take an input message and we're going to map the characters in it based on the left side and turn them into the characters on the right. And then when you get a coded message, you can convert them in by going backwards, the inverse, from right to left.
So let's say that I live in one city and Kevin lives up in the mountains somewhere and
in the woods.
Yeah, I need to communicate with him and we're doing it by
secret.
Raven. Yeah, so I'm going to go to my Ravenry and collect my strongest bird and I'm going to send a message, hello. And I'm going to encrypt this message by following my cipher. So H becomes this V, E becomes a G, L becomes, where are you?
T.
L, a T, and so on. So we end up with VGTTX, Vigitix. And I send this to Kevin via Raven. He receives
it to that poor little Raven,
yeah.
And then...
And he has this cipher on his end, so he can make sense of this. That's the only way it makes sense. So he can figure out that I was actually wasting this poor Raven on sending him the message, hello.
Like, what? Hi?
Yeah.
Hi,
and
hi, Colt.
He can do the same thing. He sends me his response back.
I'm going to send you goodbye.
Is goodbye. Okay.
So
So this is obviously not a very good approach. This is not a very secure way of communicating because it's very easy. Well, first of all, if somebody just happens to find our cipher, our coverage blown. It's very easy to figure out what we're saying. But second of all, we don't even need to, somebody doesn't need to intercept this cipher. They could just work backwards from this.
Yeah, there are patterns to find here.
Yeah, and if we're looking, if we were trying to do this, most basic, let's look at a paragraph of code. We'd look at the single letter words maybe. In English, we might look at, A and I. Those are pretty much the only 2 single letter words.
Or O if it's the 1700s.
Sure. So we look at those and then we can work backwards and figure out, okay, so this is probably I. And then we can plug that in and look, where are all the other I's? Where are all the other A's? Or vowels are the most common by far. Or S's often come at the end of words, for example. And you could write code very quickly to figure this out. It's
double
not
T's
secure.
And double L's, yeah.
So this is good for sending like messages behind your teacher's back in middle school, but that's about it.
The next step, or after a few steps, came a much more advanced version that you might have heard of, and this form of cryptography is called the Enigma code. And to code a message in the Enigma code, you use an Enigma machine.
And this was back in
World War II.
Pre-World War II and World War II. I think work started a little bit before. This is all, if you've seen the movie, The Imitation Game, this is basically what we're talking about here. Really good movie, by the way, if you haven't seen it.
It's a good movie.
So it's this much more complicated algorithm, a much more complicated way of encrypting a message, but it's the same idea. You have some message. In this case, it was developed by the Germans mainly to be able to communicate during World War II. They would basically type the message into this machine. There's a bunch of settings, different dials you would change, different settings that would rotate on a schedule, as far as I remember. Mm-hmm. And you would type the message in, and then it would light up to show you what the actual message that you are going to send is. So you would hit H, for example, and it would light up some other color, or light up another letter.
So you broadcast that on the radio, and then your U-boat captains will get the message and then plug it into their Enigma machine with the same settings, and out comes a German message.
Now, part of what makes this so hard to break is that if the Caesar cipher, you type in the letter H, for example, it's always going to be, let's say, V in our cipher. It's always V over and over. But if I type a message here, this is an online version that allows me to encode and decode. So these would be like the different dials, the rotors that we could alter. So I'm just going to leave it with these default settings. If I type hello, notice what my output is. There are two L's, the same letter, but they're not showing up here as the same letter. Or if I just type the letter P over and over and over, I'm just hitting P like 10, 20, 30 times, look at this output. It's pretty crazy. So to work backwards from this is much, much harder. Now, it's actually not that sophisticated compared to the algorithms we have today, but back then this was a monumental effort to overcome. That's what the entire movie, by the way, there's a sponsored link up here, just notice that. That's what The Imitation Game is about this really gifted mathematician and cryptographer, computer scientist named Alan Turing.
Played by Cumberbatch.
No, Benedict Cumberbatch, Kevin. So, as I was saying, with computers the way that they are today compared to World War II, the Enigma machine, the Enigma cipher would be much easier to, well, I'm actually just assuming that, but I do know that the algorithms and the things we're going to learn are currently unbroken. So what I mean by that is that the things that Bitcoin relies on, for example, to secure the ledger, there currently is no way of breaking them. So they're much more secure, they're much more advanced. Now, maybe 10, 50, 100 years down the line, that won't be the case. But currently, the cryptography that's used in Bitcoin is rock solid.
Yeah, there's a lot of people trying very hard to subvert these algorithms, and so far, so good.
So to wrap all of this up, cryptography, aside from being fascinating and cool and The Imitation being a good movie that you should see, on top of all of that, cryptography is used inside of Bitcoin, and we'll talk about how and why, and we're going to learn the specific algorithms, but just know that cryptography is what allows Bitcoin to be secure, and it's what allows miners to verify the authenticity of the ledger, to make sure things haven't been changed, to make sure that I have the Bitcoin that I say I have. It's a really integral part of the whole system.
Benedict Cumberbatch.
Oh my God. Welcome back. So one of the really important building blocks of cryptography that Bitcoin relies on all the time is called a one-way function. So a one-way function is actually a pretty basic concept, and we're going to just briefly introduce it in this video, but we'll build upon this and we'll see eventually how it relates to Bitcoin.
So first, what's a function?
Okay, well, a function is, this is going to be a kind of a wishy-washy definition, but it takes a set of inputs and relates it to a set of outputs. So if we think back to like algebra, think of a function like x squared. So you plug in an input, like let's say 3, and it goes into x squared. What is the output? We would get 9. Right? That's the right math, yes.
Yeah.
3 times 3, we get 9.
So if you plug in 4, you get 16.
Yes. Okay, so that's an idea, or that's an example of a function.
So the
Take
function,
some input and we get an output.
Yeah, the function there is x squared.
Right. So what we have here are some emoji functions. So we have one called color, and we pass in the input is an emoji, and it spits out a corresponding output that just describes the main color of that emoji. So here we have a water droplet, and we get blue. Or we have the green apple emoji, and we get green as the output. So Kevin, what is a one-way function, though?
So imagine we try to work backwards.
Okay.
So in the next slide, we just have a question mark, and we have the output of red. So given the output of this one-way function, the color function, you can't necessarily determine the input. Unlike x squared, where if you have 9, you know plus or minus 3, your input on the color function can't be determined just from the output. So for the color of red, you can't determine whether or not which emojis are red. Strawberry, tomato. You don't know which
like
one.
A red circle, a red X or something.
Like those devil faces.
Oh, yeah.
Yeah.
And the angry, like pouting face.
And this is a unique property of this type of function in that you can't determine the input from the output, but it's very easy to determine the output from the input.
So, okay, let's contrast this with something that is not a one-way function.
The
like
plus
this, plus one. So this function, plus one, you take a number and as the input, and it just adds 1 and gives that as the output. So for example, you plug in 5, we add 1, we get 6. You plug in 0, we add 1 to 0, we get 1. So if we have 6, for example, we can work backwards and figure out the input. We know that, okay, if plus 1 generated 6, we subtract 1, and we know that the input was 5. So this is not a one-way function. Here's another example. This is a one-way function. Shape is another function that takes an emoji. This time, we pass in what is this object? I haven't seen one of these in a while. A shiny circle.
I think it's a VHS.
Okay.
It's a floppy disk.
Okay. Yeah, that's our attempt at being funny.
We try.
So we pass in the CD-ROM, and we get the output is circle. But of course, there's a ton of circular emoji. Every single face emoji, happy face, slightly smiling face, all of those are circular.
You wouldn't be able to work backwards from the right side. Also here, given the is-even function.
Yeah, so we're not only working with emoji. Here's another example.
So 5 is not even, so out comes no. If we plug in 6, it's going to give us yes. But given just a yes or a no, we don't know what the input was.
Right, we can't just say, oh, my answer is yes. What was the input? I mean, there's infinite even or odd numbers.
So one more function, my favorite of all of these, is the number of legs function. So you plug in an octopus, 8.
Okay, there are only 4 legs on this emoji.
It's not an anatomically correct octopus.
So
but
you're just assuming that there's 4 more?
I think it's just the idea of an octopus. And the same way, the idea of a dolphin. This emoji is anatomically accurate. But in this way, number of legs, it's a one-way function. If you give me 8, although, you couldn't guess octopus just from the number of legs.
You could guess any spider, right?
Could be spider, yeah.
Arachnid or something.
Number of legs, dolphin, 0. That would be much harder one to guess.
Could be a snake,
a snake,
is it a dolphin,
a jellyfish.
Sure, jellyfish.
Does a jellyfish have legs?
No, absolutely not. You think those are legs?
Yes.
No.
So, yes.
So to summarize, jellyfish definitely do not have legs, but also
Sort of.
one-way functions. What do you mean sort of? They don't. There is no chance that they have legs. They have tentacles. They don't even have like a digestive system. They don't have a real nervous system. They're sacks of water, and you think that they have legs?
There could be jellyfish watching this right now. Be sensitive.
Oh my gosh. Okay, I apologize. Anyway, back to one-way functions. All that we would like for you to take away from this is that there's an idea of a function, take an input, and you get some sort of output related to that input. A one-way function is a special case where you cannot work backwards. So if you only have the output, you can't figure out what the input was. And this is going to be a really important concept once we talk about cryptography and how it relates to one-way functions and how that relates to Bitcoin. I think it will make more sense. But all that will say, Bitcoin makes use of some very special one-way functions.
Yeah, we'll see why that's valuable in some of the coming videos. Welcome back. So in this video, we're going to talk about a sort of intuitive application of one-way functions. And it's a function that you might be familiar with. It's called a thumbprint. So a thumbprint function takes as its input a human being, and as its output, it provides the thumbprint. Thumbprint function isn't a real thing. It's just a concept. It's a relation between an input and an output.
Okay.
So,
and for our purposes, are thumbprints all unique?
Yeah, for the purposes of this video, let's just pretend that all thumbprints, each person has a unique thumbprint.
Okay.
I think it's 1 in 50,000, but in general, for the course of this video, let's consider them all unique.
Okay. So, for example, this green woman is the input, and this output over here, we have this, I used to know the name for these shapes. I took a forensics class. I think it's a whirl.
For the whirl.
Yeah. Anyway, there's whirls and arches and something else.
So this is a one-way function, though, because given just a fingerprint, you can't produce the actual human being that it came from. So we're going to begin with a little story.
Yeah, this is a harsh transition to a side of a knife.
A knife. So there's been a crime, and we're at a wedding. Someone stabbed the wedding cake. and someone cut the cake too early.
Yeah, I was gonna say that's the point, right?
Yeah, no,
Stabbing
someone did
a
it
cake is
before
just serving it.
the bride or the groom did.
Okay.
But there's a clue, and you'll see on that knife there is a fingerprint.
Okay, a bright orange fingerprint.
A bright orange fingerprint, yeah, colored for visibility.
Oh, there we go. There's a zoom in on that.
So we look at the fingerprint, and we want to determine whose fingerprint it is. And if we determine whose fingerprint it is, then we can determine who stabbed the cake, who cut the cake too early.
Yeah, and for our purpose, how many guests are at our wedding?
There are 4 of them.
Including one massive baby.
Colorful, one
baby.
person has a hammer and a hard hat and a large baby.
Yes.
And we want to determine which of these 4 people actually cut the cake. And we're going to use our one-way function to do that.
So, wait, why is this a one-way function? How does that...
we have the output of a one-way function, and we can't work backwards from that fingerprint. We can't determine what the person actually looks like with just their thumbprint.
Right, you can't just stare at the thumbprint and say, oh, I know who this is.
Yeah, this person has blue eyes. This person has red hair.
Right.
So we're going to take this fingerprint, and the way we can actually use a one-way function to determine who cut the cake is by plugging everybody into the actual thumbprint function.
So that just means thumbprinting everybody.
We're going to fingerprint everyone.
We're going to go around and we're going to, check against these people's fingers. We're going to compare each thumbprint. I guess technically we don't know that it was only a thumb. It could have been any fingerprint, but let's just say
let's pretend
in our
we
world,
know it's
you
a
only
thumbprint.
have one finger.
And at this point, the wedding is ruined because we're thumbprinting everyone. And right now the attention is on finding a criminal amongst us. So we've plugged our fingerprints. We plugged everybody into our fingerprint function, and we compare the output, and we see that there's a match. It's this person on top. And we've color-coded it, which makes it even easier to see. But the fingerprints match. And now we've determined, we haven't worked backwards from the fingerprint to create a person, but we've plugged all the guests into the thumbprint function and compared their outputs with the actual clue that we had.
Right. So that's what this slide shows.
Yeah.
We don't go from the fingerprint back to the person. We have to go from the person to the fingerprint.
Mm-hmm.
So it's a one-way function. So another maybe actually real-world example that makes a little more sense is a lot of modern phones have thumbprint or fingerprint scanners. So, you verify who you are, your identity, by scanning your fingerprint to unlock the phone. But that only works because when you set the phone up, you had to go through and scan your fingers and, do them one by one or set up individual prints. But you had to go through and basically show what your fingerprint looked like.
So the thinking here is that your phone, instead of scanning your whole body cell for cell, your phone just trusts that the fingerprint function on you will output something that's unique to you. And that way it can detect an imposter. It can detect that it's looking at the real you.
The reason we're doing any of this is that it actually does relate to Bitcoin, and fingerprinting in general is something that, so we've been talking about thumbprints in the real world, and I actually think it's kind of confusing because what we're now going to transition to is talking about something called fingerprint functions, which are real functions that your computer can run code that will basically take some sort of input and return some sort of unique output.
Yeah, so in the same way that you fingerprint a person, you can also fingerprint data on a computer. So pictured here is Ubuntu, the operating system, as a file. You can take the fingerprint of that file to detect that you're looking at the real file. We're going to explain that in greater detail in the next video.
And as a small teaser of how this relates to Bitcoin, fingerprint functions are used to secure the data in the blockchain to make sure that things haven't been changed or tweaked.
So on the blockchain, we should be able to detect imposter blocks or imposter edits to the blockchain.
Okay, we're getting ahead of ourselves. Next, fingerprint functions. Welcome back. So in the last video, we briefly touched at the very end on the idea of fingerprinting a file or a piece of data. This is something that's really commonly done. We're not talking about human fingerprints anymore. We're talking about files, images, pieces of data, parts of the blockchain, where anything on your computer, really, any piece of data, you could take and run it through a fingerprint function and get some sort of unique output, something that corresponds to that one input. So first, we need to talk about a little bit of terminology. So there's two terms, hashes and fingerprints, or hashing functions.
There's actually a third term called message digest, and we're going to all use these interchangeably in this course. technically the output of a hash function is a fingerprint. So the way we would look at our thumbprint example from the previous chapter, our hash function would be the actual thumbprinting process. The fingerprint would be your fingerprint on the piece of paper.
Okay.
But so in this course, we're going to use them interchangeably. You can be comfortable doing that too. Unless you're talking to a mathematician, it's safe to use them interchangeably.
Okay, so returning to this slide, what we're showing now is that we have any file. We're using, if you're not familiar with Ubuntu, it's a very odd sounding term and it doesn't really matter. Just replace this with any file, a contract you've signed, a PDF, a Word document, a text file, it doesn't matter. So any file, you plug it in to one of these fingerprint functions, and we're going to show some specific examples on the next slide. And their only job is to return some sort of output, usually a really long string of numbers and letters, that corresponds to whatever you fed it, whatever the input was.
And although it's long, it's not going to be as long as the input.
Well, of course, yes.
In the same way that your thumbprint is not informationally as large as your whole body, this fingerprint right here is not informationally as dense or is not as large as the actual input file.
Well, if we were to look at this file itself, not what it looks like as an icon, not the text, not the title, but the actual data behind it would be, I don't know how many pages and pages of code of zeros and ones or of a long string of numbers. We're talking hundreds of thousands of characters or millions of characters. But if we take a fingerprint of that massive, massive piece of data, we can distill it down to basically 64 characters, depending on the fingerprint function we use. But we can slim it down to get this unique identifier that corresponds to that long string, but it's only a couple, 32, 64, roughly number of characters, much, much shorter. So there are a bunch of, you can probably imagine this is hard to do, to write the algorithm, the logic to do that, but there are three famous or commonly known examples of these fingerprint functions that we're going to discuss.
We're going to cover them really quickly. The first one is the MD5 function, and that was written in 1992. That's a fingerprint function that's very widely used. The problem with it is that in 2004, computer scientists discovered a way to cheat it. And that we'll describe what that actually means, how you would cheat a fingerprint function, but it makes it less valuable as a tool to determine whether or not something is unique or verify its authenticity. The second one is called SHA-2.
So in 2002, SHA-2 came along, so these are all created by, this isn't, as far as I know, these aren't individual people working away. This is organizations.
Yeah, they're groups.
So
very often governmental.
For SHA-2, the group that put this together was called the National Institute of Standards and Technology, NIST, apparently. And this fixed some of the problems that were present in MD5. A lot of the security issues were patched or changed in SHA-2. So in today's world, SHA-2 is really widely used, especially online for internet security. And an important note, I guess we didn't star this, but we should highlight this because SHA-2 is what Bitcoin actually uses, and we'll go into that and explain it. But out of these three, SHA-2 is the one that Bitcoin is built with.
And Bitcoin really relies on the security and the soundness of that algorithm. If it were to be broken in the same way that MD5 has been broken, it wouldn't just be Bitcoin that has problems, it would be virtually all of the internet application infrastructure.
Right.
You'll definitely hear about it in the news if that ever happens. But we also mention a third iteration called SHA-3, Ketchak.
Well, yeah, I don't actually know if it's pronounced. I mean, Kevin thinks it's Ketchak. It might be Ketchak.
Ketchup, right?
Kekak.
Kekak.
Anyways, it's this family of algorithms of hash functions.
So SHA-3 is another family of hash functions, and it was developed in 2009. It's faster than SHA-2, and it's more secure than SHA-2, and a lot of technologies are moving into SHA-3. That doesn't mean SHA-2 is obsolete, but if you're building a new application, very often people are going to err on the side of this newer version, SHA-3.
And along with that, newer cryptocurrencies that we haven't really talked about, but things that have popped up after Bitcoin, many of them rely on SHA-3.
So hint, Ethereum uses SHA-3 for its internal hashing mechanism.
Right. Okay, but we're going to talk about SHA-2 right now because that's what Bitcoin uses.
So SHA-2 is actually a family of hash functions. You can actually, there are some parameters when you plug it in. And pictured here are SHA-256, SHA-384, and SHA-512. These specify the size of the output in bits.
Right.
So very often you're going to encounter SHA-256, But there is a more complex version that outputs twice as much information, twice as much entropy. In the case of Bitcoin, we're going to be using the 256-bit. That means every time you use SHA-256, the output is 256 zeros and ones.
So, remind us a bit. Well, you just said what I was going to ask you.
It's
a bit is
a
0 or a 1. And so imagine we have 1,000 characters, a piece of data that is 1,000 bits. We run it through SHA-256. It's going to slim it down to 256 ones and zeros. If we ran it through SHA-512, it slims it down to 512 ones and zeros. So we plug in something and we get an output. And what Bitcoin does is it uses SHA-256. So the output is going to be 256 bits. But that's ones and zeros. And we'll see that actually we can display that in a slightly better format where we use characters, base 10 or base 56.
Things that are easier to read.
All right, welcome back. So in the last video, we introduced the idea of a fingerprint or a hash function, which basically is a function, some very fancy code, a long algorithm that takes some input file or some input string of data or even just a character of text. It really doesn't matter, but some input on your computer, and it spits out something that looks like this potentially. So this is SHA-256, one of the algorithms we talked about. Remember, there was also MD5 and SHA-3, Ketzak, whatever you want to call it. So we pass in some piece of data. This is imagine it's the equivalent of a human. We take a human and we take their fingerprint, a thumbprint. So regardless of the size of the input, whether we're talking about hello, which is just a couple characters, or it's an entire operating system file, it's the entire Bitcoin blockchain, whatever it is, the input doesn't really matter as far as the size of the output. It doesn't change it. The size of the output of SHA-256 is always 256 bits. So this isn't 256 ones and zeros. What we're looking at here is hexadecimal, which is base 16 instead of base 2, which is binary. It's it's a tangent, but all you should know if you are unfamiliar with either of those terms, this is a more condensed format for displaying it. But this converts into 256 ones and zeros. So whether we take hello or goodbye or some of the other things we'll show, we'll do it with an image, we'll do it with an actual file on my computer, you'll see we always get 256 bits at the end.
Let's first talk about a few properties of hash functions before we show you a demo. The first property is determinism. So that means given the same input conditions, you'll always get the same output. So regardless of where you run your SHA-256, if you plug hello in, you're going to get the same output.
Okay. So on this slide, we actually have 3 examples, 3 different hash functions and their outputs. We have MD5, we have SHA-2, and then SHA-3. The outputs are all very different based off of the same input. But every time, let's say we're working with MD5, if I run hello through MD5 on my computer or on Kevin's machine or on somebody's computer on the other side of the globe, we'll always get this output.
Yeah, regardless of when and where you run it.
Unless something was changed with the input. But assuming the input is always the same, we reliably get the same output. So we're talking about SHA-256, so our output looks something like this. We would always get this whenever we run hello as the input.
So per our analogy, your thumbprint tends not to change throughout the course of your life. If you actually hold a knife and cut a cake, you leave a thumbprint. And then when you're fingerprinted, when you are thumbprinted later on, you're going to have the same fingerprint. That is the determinism in our analogy.
So the next property is that whatever the output is, it should be quick to compute. So these functions are used all the time. Like we talked about how they're used in internet communications. You don't want to have to wait 10 minutes for something to run in between you viewing a web page, for example.
And in the same way, you can thumbprint someone very quickly. You just put their finger in ink and then on a piece of paper.
Right. Unless they're being unruly. Then you tranquilize them and you fingerprint them while they're passed out. Anyway.
Okay, property 3. They should be infeasible to reverse. So this is going back to it being a one-way function.
Right. So these are supposed to be one-way functions, which means we know what the input is and we can figure out what the output will be, but we shouldn't be able to take the output only and figure out the input. And obviously, us as humans looking at this, if I covered the left side of the screen, there's no way any of us could guess what generated this result. But even computers shouldn't be able to sit and crunch this for decades and decades and figure it out. They shouldn't be able to go from this and reverse it. Now, I mean, what you could do if you could run SHA-256 on every word in the English language and then compare the result, but you couldn't work backwards. You would have to do this crazy brute force approach.
Yeah, so this is like finding the culprit at the wedding.
Yeah. Well, we only had 4 people there.
Yeah, in this case, you would have to hash every single possible string that you could provide to SHA-256.
Yes, and we're talking about
feasible.
We're talking about tiny words here, but when we talk about actual, like how it relates to Bitcoin, we're going to work with much larger pieces of data where it's impossible.
Big data.
Next, a hash function needs to be infeasible to collide. So what does that mean?
So this is going to prove very important in actual Bitcoin mining explanation. For hash functions, it should be very difficult to find 2 inputs that give you the same output. So if you're looking at all these numbers here, you'll see how wildly different hello and goodbye are. It should be the important property is that it's extremely difficult to find. For example, if we look at the right side of hello, it'd be very difficult to find another word or another piece of data that gave us exactly that.
Yeah, it's just infeasible is, I guess we should mention it's different rather than impossible.
Yeah,
it is possible that you could have a collision, but it's supposed to be the way these algorithms are written. And again, the actual code behind them is crazy, the logic that it goes into it.
Yeah.
But it should be very, very, very unlikely for you to have one file and another file, no matter what's in the files. And if you hash them with SHA-256, for example, they should be nothing alike.
So if, back to our thumbprint example, if you have somebody with a thumbprint, which many of us do, it should be, and it is very difficult to find somebody else with an identical thumbprint. It's possible.
Yeah, that kind of falls
out
short
there.
though, because that's like 1 in 50,000 or so.
Yeah.
When we're talking about collisions here, we're talking about 1 in like trillions and trillions.
Bajillion.
Yeah, sure. I'm going to need to see a source for that, Kevin, on the bajillion. So finally, with the hash function, a small change in the input should lead to a big change in the output. For example, if you take a look at the bottom half here, if we have goodbye, we've highlighted the end, the last, 6 characters. Just focus on those. And I'm going to just make a slight change to goodbye. I'm just going to add an extra E. And look at that massive difference. Everything changed in there. And one more E, another very strong difference, large difference. However, when we're talking about changing a single character out of the word goodbye, that's actually kind of a big change because goodbye is only, 7 characters?
7.
Yeah, so changing 1 out of 7, that's a pretty big change. So let's do something that's a much smaller change. Here we're taking an image. So remember that behind every image is a bunch of numbers, 1s and 0s. So imagine we change 1 pixel on this image. So this is the first input. This is what we get. Again, we've highlighted it here. But
just look at the bottom right.
Yeah, it's just too much to try and analyze this whole thing. So we changed 1 tiny pixel right there, and our output is completely different. It's not like there's been a slight change. It's completely radically different. They're not at all related. And that's important. That's how it's supposed to work, that a small change in the input leads to a large change in the output.
Yeah, if you were to do, here they are side by side. If you were to take all of Moby Dick and take the fingerprint of it, and then you were to take all of Moby Dick and remove 1 period or add 1 stray apostrophe, the fingerprint would be entirely different.
We should do that as an example.
Okay, let's do that.
Okay, we're going to do that next. Real quick, before we wrap up, this is another thing that we didn't, not enough to make a whole video on, but it's important to cover. So we talked about how the output, like if we take a look at one of these outputs, it is a mix of letters and numbers. But actually what it is, it's a very large number, but we're not displaying it in base 10. We're not using the normal number system we're used to as humans to count, at least in the Western world. Some other places use other bases to count, but in the Western world, we use base 10. What we have are also the letters A through F, which are actually numbers. So when we talk about hexadecimal, it's base 16. So the numbers no longer go from 0 up to 9 that you could have. If we're talking about a single digit, the largest single digit number we can have in base 10 is 9. When we talk about base 16, you actually go past 9, but we don't have a number to show that in our counting system, so we use A to mean 10, B is 11, all the way up to F, which means 15. So every single digit in this number ranges from 0 up until 15. So for example, this is a 14, this is a 15, right? Then this is a 8 and a 4. So these are large numbers that are just displayed in a shorter, more compact format so they could fit on this slide easier, basically.
So the last thing we're going to do is we're going to add a layer of convenience for our slides. It's very difficult to look at hash outputs. Whenever we're referring to hashes, or not always, but sometimes when we need to compare the difference, a lot of the time, Colt and I are just going to compress it into an emoji.
Yeah.
So instead of showing you a long string of hexadecimal digits, we're going to actually just do an emoji. So on the top, SHA-256 is actually SHA emoji. Take the rainbow picture, out comes the unicorn. Although those are somewhat related, disregard the connection there. And if we were to change one pixel, we would get flan. I think that's flan, right?
Yeah, it's flan. Or some sort of custardy thing, whatever that is. Actually, I think in Europe it's called a creme caramel.
Creme caramel.
Anyways, so whatever it is, we get two radically different outputs, and we're using emoji rather than this and trying to, show that this is different, because this is much harder to talk about compared to nice little emoji. Okay, so that's a rough intro to hash functions. Okay, welcome back. We're now going to do an actual demo of SHA-256. So this is not something, we want to be really clear about this, not something you need to do. You can absolutely follow along if you want to, but this is not important to actually, being able to work with Bitcoin. It's just a matter of understanding hash functions and how SHA-256 works. We're going to see some cool results that we get. So we actually went and downloaded Moby Dick as a text file, mobydick.txt. You can find it online. It's really long. It's like 15,000 or so lines. Yes, 15,604 lines of text. So we're going to hash this file, but we're going to actually start with something even simpler. I'm just going to hash like my name or a piece of text. So the command that we're going to do, and this is not the only way of doing it, and I don't want anyone to get hung up on the syntax, but I'm going to do this right here. I'm going to put a string that we're going to hash, so hello. And then here's the actual part where I'm going to tell it to use SHA-256. So again, not what the course is about. This command, I'm in the command line, the terminal. If you're not familiar with that, it's okay. We're not worrying about that. So I'm going to hit enter now. And you can see I get an output. Just let's look at the beginning. 2CF, and then it ends with 824. Okay, so let's do the same thing, but change this slightly. Let's capitalize the H. Now I get something completely different. So every time I run this with that capital H, I'm always going to get that same output. All these times, I should get the exact same thing, whether my computer restarts, whether I'm doing it on someone else's computer.
And that's the deterministic output.
Right. And we're talking about every time I do SHA-256. Now, if I'm doing some other, like MD5, for example, or something in the SHA-3 family, I would get a different output, but should be the same output every time I run that particular algorithm. So now let's talk about Moby Dick. So over here, I have a file. It's called mobydick.txt. So I'm on my desktop here where that file is. If I were to look at that Moby Dick file, I just printed it out in my terminal. So here it is. It's called mobydick.txt. Now I'm going to run that exact same command. Now the syntax to use SHA-256 with a file is slightly different, but I'm just going to write it out. Again, we're not really, this isn't the point to explain all of this, but SHA-256 and then the file name, which is mobydick.txt.
And this will run quickly.
Yeah, so you could see that was a long file, although it's only text, which is pretty easy. If we were talking about, a video file or something, that's a really big file. That
takes
gigs.
longer, yeah.
But it goes relatively quick. Okay, so here's the output here, D688. Every time I run it on that file, I get the same thing. Now what I'm going to do is go change let's do a single period right here. Sure.
Let's just capitalize a letter.
Okay, how about...
Capitalize the L in lungs.
There we go, and I'm going to save it. Command S on my Mac, so it's now saved. And I'm going to go back and rerun the same command. And there we go. Look at that, not even close. I mean, we have 900B44, completely different. This is pretty cool stuff, in my opinion. I mean, just imagine trying to make this work yourself. If somebody was just like, okay, you need to take any string of data and you need to turn it into a unique or relatively unique tiny string of data of ones and zeros or of base 16 hexadecimal. How would you do that? It's pretty crazy. And that tiny change, just changing that case of that L, actually, let's just show that it's reversible too. If I go back, I've saved it, and then run it again, we get what we got before. Pretty cool stuff. So that's a really quick intro to SHA-256. That's all we wanted to demonstrate, is that it works in the properties that we described are real. Every time you run the same hash with the same input, you get the same output. You change something small, it leads to a large change. In the output, it should be quick to compute and so on. Don't worry about the syntax, but try it out if you'd like. If you don't know how to use a command line and any of that, I wouldn't try and go learn it just to do this, because we've got a lot of stuff to talk about after this. So next, we're going to learn how Bitcoin actually incorporates SHA-256 and what it has to do with Bitcoin. All right, welcome back. So for some reason, this is called hash functions in U. What should it actually be called, Kevin?
It probably should be called hash functions and safely downloading a file, but that's not as catchy and it wouldn't really fit with our typeface.
So what we're going to do is show that you can run SHA-256 on a file, much in the way that you could do it on an image here. And remember, one tiny pixel of difference leads to a very serious difference in output.
Flan.
I mean, yes, they're actually hashes, they're numbers like this, but our emojis are radically different. We're going to see the same thing with files. So what we're going to do is download a file, and this is going to be an operating system. It's called Ubuntu. I never know how it's actually supposed to be pronounced.
I think Ubuntu.
And the reason we're using this as an example is that it's an operating system, a low-level operating system, which in some ways makes it much worse if it were to be compromised in any way.
Yeah, as opposed to just an application, which might steal, I don't know, a password or two. If you were to download a compromised operating system, it could, for example, turn your camera on without your permission. It could
or
steal
just like log
everything
every
you type.
stroke you ever type.
Yeah, it could turn the microphone on without your permission. If you were an evildoer, this is how you would want to take over someone's computer.
Sounds like a great time. If you're a hacker and you have access to that, you could do so much fun stuff.
Yeah.
Anyway, so it's something you definitely want to trust that you're getting the right copy of. You're not getting an intercepted version or an altered version. So what we do is when we actually go to the website for Ubuntu and we click on the download link, we select a version, there's a little note that I'll show you in just a second that says compare to our SHA-256 file.
Yeah, so when you download the file, it says, hey, take a fingerprint of this file and you should see exactly this output.
Right.
And the thinking is if somebody were to have taken over the website or taken over the download, then they wouldn't be able to produce a file with the same fingerprint. They would have modified the file and the output fingerprint would be totally different.
Just like this. Now imagine instead of an image, it's a full operating system. Even one character of bad code or of some sort of bug or hack in there, that's a way oversimplification, but even one character could lead to two radically different fingerprints. So I'm on ubuntu.com and I'm going to go over to downloads. And then you could do this for any of them. We're going to do Ubuntu Core. It actually doesn't really matter at this point. I'm pretty sure all of them offer it, right?
Yeah, all of them will have fingerprints.
And we're going to do Raspberry Pi. Again, what we're actually downloading doesn't matter. All that matters is that it's something you absolutely want to trust. You don't want to get a bad copy of. So if you look at the installation instructions, first we're going to do, what did we decide? Raspberry Pi 3?
Yeah, Raspberry Pi 3 for Raspberry Pi 3
Here, let me make
stable.
this a bit bigger.
Yeah,
Ubuntu Core 16 image. Okay, so this is what we're going to download. Now, notice down here, you can verify the integrity of the files using the SHA-256 sum. So I'm going to open that, and I'm also going to start this download. And we'll see you in a second once that finishes. So now I'm looking at the SHA-256 sum file that they linked, that they said verify the integrity of your files against this. So it's a really simple file. There's 6 different versions
and 6 different checksums.
And 6 different results.
Yeah. Oh, checksum is also another term. So you can use these all interchangeably in this case. Checksum, message digest, hash, and fingerprint. They all mean the same thing in this context.
Yeah, it's just the output of SHA-256 on these files. So if what we downloaded, as you can see, it's still going, is the Ubuntu Core 16 Pi 3, right? So that's right here. So we're going to look to make sure when we fingerprint that file, the download that we just finished, that we get this result. So let's just remember this for now. 3072. Just focus on that. 3072. Okay. So I'm going to use my terminal here to actually do this. If you're not familiar with navigating in the command line, we're not going to teach it right now, but here's the file itself. So this is the download Ubuntu Core 16 Pi 3.img.xz. So we're going to, before we open this up and install it and basically, unleash whatever is in there, good or bad, we're going to double check that it is what it's supposed to be, that nobody intercepted it along the way or added some bad code into it. because that would radically alter the fingerprint. Okay, so one way of doing this, there are many different ways of actually running SHA-256, but we're going to do what we did earlier. So OpenSSL DGST SHA-256, and then the name of the file. There we go. I just did tab to autocomplete.
And this will happen pretty quickly.
Yep. So you're going to hit enter, and
This is a pretty big file. I think it's what, 200 megabytes?
okay, here we go. All right, we can tell already it's right, 3072. But if we wanted to just double check, I'm going to copy this. So here's what we got as a result, and this is what we were looking for. So we compare them side by side, perfect match. So that tells us that no changes were made to the file. Now, it's possible that somebody did intercept it along the way, but they didn't do anything to it, because we would get a very different output if there was even a single space. Remember what happened with Moby Dick? A single, what did we delete?
Apostrophe?
No, we capitalized the letter.
Oh, we capitalized the letter.
And that changed the entire hash, the entire output. So if anything happened, we would see a massive difference. Not to mention the fact that really any malicious code is going to be more than a single character. That it takes more work to really do anything damaging. So we'd see a radically different output. And we don't. So we can trust this now and go ahead and install it. Except I have no use for Ubuntu and I don't have a Raspberry Pi, so I'm not going to.
And a side note, for those of you who have also noticed that there's a possibility that someone could have intercepted the actual fingerprint on the website. So somebody could have taken over the website and changed both the file and the fingerprint. There is a way, using concepts that we'll describe in this course, to prove or to indicate that the actual fingerprint was created by the real Ubuntu developers using something called a digital signature.
Okay, you're scaring everyone, Kevin. So what Kevin's alluding to, yes, somebody could actually intercept the Ubuntu website or fake the Ubuntu website and put their own fingerprint up there and say, oh, this is what you're supposed to get when you download the file. But somebody could actually be, have hacked the original download, changed it, put malicious code in there, and then also taken the fingerprint of that, then put that on their fake website, and then confuse you, and we're now being completely hoodwinked into thinking that everything's good.
Down the rabbit hole.
Yes. So we're going to see how to actually verify that it was Ubuntu who posted that in the first place later on. All right, welcome back. What are we talking about, Kevin?
This one is called hash functions and passwords.
Yeah, we can read. What are we actually talking about?
We're going to talk about hash functions and passwords.
Oh,
We're going to talk about how you can use fingerprints, hash functions, to secure passwords when you store them in a database.
Okay, and when you say when you store them, we also are talking about when you sign up for a website, any website that takes security at all, I mean, not even seriously, that just even acknowledges the existence. The bare minimum that any website needs to do is not store your password as plain text.
Mm-hmm.
But that's still, it comes up every so often. You hear about certain websites that do it. I think nowadays it's so shameful that you don't hear about it. So let's talk about why that would be a problem first.
Well, if a website did store your password as just plain text, then the developers at the website and somebody who hypothetically broke into a website would be able to just look at the database and see your email address, which would be your username, and then see that your password was ABC123.
Right.
And that'd be sort of useful to a hacker or an evildoer because they could just go to another website and try your email and password combination. Most of the time it wouldn't work, assuming you have a different password at each website, but many people don't.
Right. Yeah, it's just, that would be terrible. So rather than storing your password as text, most developers with a brain are going to hash your password, most likely with some variant of SHA-2 or SHA-3, take the result, like we have over here, and store that in the database. So we might have something like this in our database. If somebody, well, first we have a user or a username or an email or some unique identifier on the left, and then on the right, we have the result of hashing their password. And once again, we just highlighted the last couple digits to make it clearer, but these are all unique. So first of all, this is an improvement already because if someone gets access, they hack the database, it's compromised, they get every single row in there. All that they see are the results of hashing the password. They don't actually know the password. And remember, it's a one-way function. That's like the whole point of it. So you can't work backwards from this.
And you can't go to Facebook and type in Montana and the hash of a password.
Right.
Because Facebook is going to in turn hash what you provide. It'll become the hash of a hash.
Right. So let's go through that process. But rather than saying that we have some malicious actor, let's say that Montana is trying to log in And Montana just can't remember her password.
She forgot her password.
And she uses like 3 or 4 different ones. She's just going to guess them. So the first thing she does is type her password ABC. Now, there's no password length limit on our website, or minimum password length. So that's actually not a good idea because it does make it easier to guess, and we'll talk about why. But let's just say that she can have a 3-digit password. So she guesses ABC. That's one of her favorite passwords. Well, what we do is we hash it. We use the same SHA-256. We get the results, and we're going to compare that to what we have stored in the database for her password. So we're basically hashing both and then comparing. And this is not a match, is it?
Nope.
Okay, so what'd she do next?
She types in her next password. Her next favorite is DEF.
Very creative.
So this one outputs C2717B.
At the end, at least.
So the fingerprint there does not match the fingerprint in the database. So we know
can't log in.
We know the input doesn't match. We reject her password. Next one, HIG, her third favorite password, 10A1BO. That's a negative, doesn't match.
Okay, she's getting, let's say there's only 4 attempts on our website. She's going to lock her out.
She's getting frustrated, and her last guess, KLM, 4D2 3C4. And what does that say to us? It's a match. What that shows us is that when she signed up and we fingerprinted her first password, her original password, we saved 4D2 3C4. When she tried to log in just now and we fingerprinted her attempt, we get 42 3C4 also,
right?
Which indicates the same input, independent of really any meaning of the output.
Right. Oh, Kevin, we forgot. We have a little...
Oh, isn't that nice?
We have a highlight there. So one thing that we haven't discussed is that just storing a hash password on its own is not enough to prevent someone from ever getting in, because especially if we're talking about super short passwords, like let's say a website allows you to have a 3-digit password, all that a hacker has to do is figure out what hashing algorithm you're using, and most of the time it's going to be SHA-2 or SHA-3, some variant of that, and basically write code. I mean, there's some more sophisticated ways of doing this, but the dumbest way would be to just write code that takes every combination of 3 letters to start, if that's the minimum. And it just runs that through SHA-256 and compares it to what it got in the database.
AAB, AAC, all the way up to ZZZ.
And it keeps going. So this only works if the hacker has the password hash. But if they know what they're aiming for, they could just have a computer going for days on end, potentially, trying to guess it. But then there's optimizations that can be made because there are, more common passwords. There are patterns people like to type, certain numbers people use, things that, there's just words, for example, that are used rather than random letters. So this is why it's always better to have a longer password, why sites force you to use numbers and special characters and things that are harder to guess. You couldn't just hook up a simple, password guesser. There's some really, if you go on GitHub, you can find some simple examples. But anyway, the point is, storing a password hash is much, much, much better than just storing plain text, but it doesn't necessarily guarantee that nobody could ever guess the password. It just makes it a lot harder.
Yeah, and if you are using this information towards building your own website, there's also some other sort of safety mitigations on top of using hash, or something called assault. And that's not in the scope of this course, but it's important to include that because it is possible to work backwards if you allow, for example, 3-character passwords.
Right.
Or if you permit people to choose their password as some simple single word, all lowercase.
Or a really common thing is to not allow people to use any part of their username inside of the password, because then that's going to be most hackers' first guess. If you allow that, they have the username, let's just try a variant of that. Anyway, we are not security consultants, so this is purely educational. Don't sue us if you get hacked, please.